Number 3 is a little bit different than the last two. Not a lot different. The difference, if you look at this diagram and think about what the difference is. In the last diagram, there was something hanging over here, and the wire went all the way to it. In this one, the wire only goes this far, and then this hanging object is over here. So it says it's a sign. It says the sign has a mass of 40 kilograms. And so if I take 40 kilograms times 9.8, I'm going to get 392 newtons. And if I take 15 kilograms times 9.8, I'm going to get 147 newtons. So I'm going to come over here and draw my force diagram. I have my sign. It has 392 newtons, which is acting in the downward direction, of course. That's gravity. Of course, I have the tension on the string, so I can draw that in. And eventually we will want the x component and the y component for that. And then I have the mass of the pole itself, which is this 15 kilograms, which comes out to be 147 newtons. And I need to think about where should I put that from. If you look closely at your diagram, it shows you that this distance is 3 meters, this distance is 2 meters, so the whole thing is 5 meters long. And so I'm going to put my vector for my mass of the pole here in the middle at 2.5 meters. And so that is where I'm going to put my 147 Newton. Again, it's acting downward. The force of tension, of course, is acting in the upper, up and to the left, so there is an upward component of it, and there's a leftward component of it. Okay, so we've done our force diagram. We now need to do calculating the tension in the cable. Again, it's kind of hard to read here, but the angle is a 45-degree angle. So we're going to have to set up our equilibrium equation where we add up all the torques and set it equal to 0. So again, we have 3 items that we are having to, 3 forces that we have contributing to our torque. Okay, so my pivot point is here, where I'm naturally going to see that occurring as a pivot point. I've got the 147 newtons going downwards at halfway, 2.5 meters. I've got my 392 newtons, again acting downwards at the full distance away, which is 5 meters. And then I've got my force of tension in the y direction, and that is here. And if you can look at your diagram, that is marked as being 3 meters away. So that's what that is. So now I'm going to take my calculator and I'm going to work this out, and I'm going to find the force of tension in the y direction. All right, so here I found my force of tension in the y direction to be 775.8 newtons just by solving that equation. However, the question was asking for the tension, not the force of tension in the y direction, but the actual force of tension. So once again, we're going to have to use trigonometry to find our force of tension. So take a few seconds to look at that diagram and see how you would set that up. All right, so what I did is I used sine of 45. You could have used radical 2. You could have done various things here, but when I did that, I came up with a force of tension as 1,097.2 newtons. Now the next question asks us to calculate the vertical force exerted on the pole where it connects to the wall. So if they're asking about the vertical forces, I'm going to use the sum of the y forces is equal to 0, the equilibrium in the y direction. So we need to look at all the things that are acting in the y direction. And so the question they are actually asking about is right here, like, is this wall exerting a vertical force on the pole? Like a minute ago, we were talking about, is there friction? Is there a bolt? Is there something that's exerting a force in the y direction? That's what they're asking about here. And so I need to look at all of the various y direction forces. And so when I look at all my y forces, I have the force of the wall in the y direction. I have the force of tension in the y direction. I have the force of gravity from the sign. That's kind of messy, but that's what that says. Force of gravity from the sign. The force of gravity from the pole. All right, the force of the wall in the y direction, that's what I'm looking for. The force of tension in the y direction, we've already discussed, is 775.8. We figured that out a second ago, and that's working upwards. The force of gravity from the sign is negative 392, again working downward, so it's negative. And the force of gravity from the pole is negative 147, working downwards because it's negative. So now we just need to add these up and figure out what the force of the wall in the y direction is. All right, so when we figure this out, we get the force of the wall in the y direction is 236.8 newtons. And if we look at our original equation here, that must be acting down because these numbers fall short of 775. And we've got 775 pulling up. And so this wall, in this case, must be actually acting down, which is a little bit strange, but that sort of means that we have 236 newtons that we can still apply to this where it would not fall down. You know what I mean? Like this amount is still available to us to hang something bigger on here or to move this or what have you, but we've still got some force to give. And so the force on the wall, the vertical force from this wall, it's actually pushing it down. It's stopping it from rising up, like scooching up. That's what that force is. Okay, we will do the next example, number 4. We will modify it a little bit, and it will be in a separate video.